Okay, still moving along here in section 4.4. Example 64 is just kind of a fun little example using this information about the first and the second derivative of a function and going back now to talk about particle motion along a straight line. Because we talked about that, we understood that if you have a position function, the velocity is the first derivative of position and acceleration is the second derivative of position. But now we can also talk about using the understanding of the first and second derivative more so and describe, okay, what's going on with this and which way is it moving? Is that particle speeding up or slowing down, et cetera, et cetera. So let's go through this step by step. So we have the position function for t greater than 0, thinking of t as time. So if I take the first derivative, I get velocity. So I get 6t squared minus 28t plus 22. Now, first thing you'd want to do is look at where the velocity is equal to 0. That would be where the first derivative is equal to 0 of a function, which gives us critical points. So this actually is a quadratic, which actually can be factored. It's not too bad. So you get that at t equals 1 and at t equals 11/3, we have critical points. Now, for a particle motion in a straight line, that means where the velocity is equal to 0. The particle has come to a complete stop at these critical points. And then recall that acceleration is the first derivative of velocity or the second derivative of position. So acceleration in this case would be 12t minus 28. If I set that equal to 0, I see that I have what's called a possible inflection point at t equals 7/3, right? Solve this for 0. 6t minus 14 equals 0. I get t equals 7/3. So that's a possible inflection point because that's where the second derivative, or in this case acceleration, is equal to 0. Okay, so now go through and let's describe the motion. So the first thing we're going to do is look at the first derivative. First, do a first derivative test, right? I can see that the first derivative is always positive between 0 and 1, which means it's an increasing function, which means velocity is positive, so the particle is moving to the right. Between 1 and 11/3, the other critical point of 11/3, the velocity, or the first derivative, is always negative, which means the particle is moving to the left. And then after 11/3, the velocity, or the first derivative, is positive, which means the particle then again moves to the right. So notice what happens. The velocity becomes 0 at time 1, stops. The particle turns around and goes back in the other direction along the line. At time 11/3, the particle then stops again and turns around and goes back in the other direction along the line, whichever line it's along. Okay, then what does the second derivative tell us? Well, the second derivative tells us acceleration, so we have a possible inflection point at 7/3. So what's going on with the second derivative? We need to look at the second derivative on those intervals around its inflection point. So that means that the first derivative, velocity, is a decreasing function over here because the second derivative is negative, right? So the first derivative, velocity, is a decreasing function. And then the first derivative over here is positive, which means that the velocity is an increasing function. I'm sorry, second derivative is negative here. Second derivative is positive here. Second derivative being negative tells me first derivative is decreasing, which is velocity is decreasing. Second derivative positive here means that velocity is an increasing function. So you put these all together, and the way you think about whether a particle is speeding up or slowing down is when the velocity and the acceleration are different signs. So notice here that velocity means the particle is moving to the right because its first derivative is positive, which is velocity, means it's moving to the right. Acceleration, the second derivative, is negative, which would want to push the particle back that way in the negative direction. So velocity is working against acceleration, which means the particle is slowing down. At time t equals 1, the particle stops and turns around and goes back in the opposite direction on the line, and acceleration and velocity are the same sign, so the particle is speeding up. Then at times t equals 7/3, the acceleration changes sign to positive. Now the particle starts to slow down again. The velocity is negative, the acceleration is positive, so the particle is slowing down. At time 11/3, the particle stops, turns around, goes back in the other direction. The acceleration is also positive, so now it's going to speed up forever. And this is just like a graphical picture of that happening. Okay, I hope that makes sense.